Hi, everybody. Happy Cinco de Mayo. We are continuing our study of gases today, and we're going to focus on the gas laws. So, studying gases involves manipulating some major characteristics that they have in common. These characteristics are pressure, temperature, volume, and the actual number of gas particles. So depending on the gas law we talk about, one or more of these characteristics will be manipulated. Okay, so the first law we'll look at is called Charles's law. And here is the equation. Initial volume, or volume 1, over T1 equals volume 2 over temperature 2. So notice that pressure and the number of particles is not part of this equation, so we assume that they are constant. It's very important that whenever we solve gas law problems that we always use temperature in kelvins. So, what is the relationship between temperature and volume? In this demonstration from NASA, you will see that as temperature increases, volume increases. I hope that makes sense. If you increase the temperature of a gas, the particles are bouncing off of each other more rapidly. Likewise, if the temperature is decreased of a gas, then the volume of that gas will decrease as those particles get closer. Okay, so let's look at an example problem for Charles's law. The volume of a gas is 300 liters at 227 degrees Celsius. Assuming that pressure and number of particles remain the same, what volume will the gas occupy at 27 degrees Celsius? So as a reminder, right, we have V1 over T1 equals V2 over T2, and temperature is always in Kelvin. Okay, so in this example, they've got it in Celsius. You need to convert Celsius to Kelvin. I'd like to remind you that in table T of your reference tables, we've got that right here. So you will note that 227 degrees Celsius is going to equal 500 Kelvin, and 27 degrees Celsius is going to equal 300 Kelvin. So let's put in our numbers. We started with 300 liters of a gas. The temperature it is at 500 Kelvin. We are trying to determine the final volume of that gas, and we know that the temperature decreased to 300 Kelvin. So if we have a decrease in temperature, right, we would expect a decrease in that volume. And when we cross multiply and then divide, we're going to get V2 equaling 180 liters, which makes sense. Okay, so let's move on to another gas law, and that is Boyles Law. And in this case, we're comparing pressure to volume. So the initial pressure times volume will equal the final pressure times volume. As a reminder, we do not see temperature and number of particles in this equation, therefore we assume they are constant. So what is the relationship between pressure and volume? So as you can see in this demo from NASA, as pressure increases, volume decreases. Okay, so now we're ready to look at an example problem demonstrating Boyles' law. So, a storage container holds 400 liters of gas at 2 atmospheres of pressure. If the pressure is increased to 5 atmospheres at constant temperature, what will happen to the volume of that gas? So let's look at this in context of the equation here. The initial pressure is 2 atmospheres, and the initial volume is 400 liters. The pressure is increased to 5 atmospheres. What will the volume be, the final volume? So to isolate that, right, we're going to divide both sides by 5 atmospheres to isolate volume, and you're going to find that V2 equals 160 liters. And that should make sense, right? That if we start at a lower pressure, we're going to have a greater volume. As we increase pressure, we're going to decrease that volume. Okay, so let's look at the combined gas law. This gas law is found in table T, right here. And it is very handy because Boyles and Charles's law are derived from this gas law. And if you look carefully at the equation for the combined gas law, you can recall what Boyles and Charles's gas law equations would look like. So we have P1 V1 over T1 equals P2 V2 over T2. My color coding is meant to help, hopefully, for you to realize that P1 times V1 equals P2 times V2. If I cover that bottom part, this is Boyles' law. Now, if I look here, that V1 over T1 equals V2 over T2. So if I cover the pressure, we have Charles's law, and that makes the combined gas law. Now, algebraically, if we want to isolate T, the temperatures, we can multiply this side of the equation by T2 to eliminate the denominator. And likewise, we can multiply this side of the equation by T1 to eliminate that denominator. And we end up here with this. So here is an example of the combined gas laws that you would get. You're going to get a lot of information in these problems, okay? Because you have 6 bits of information total. You're going to get 5 out of 6 of these. So when we look at that combined gas law example, a gas occupies a volume of 444 milliliters. Doesn't matter if this volume's in milliliters or liters, by the way, as long as it's consistent in the problem. This is already in Kelvin, so we don't need to convert to Kelvin. But if it were in Celsius, we would. At 273 Kelvin, that volume at that temperature, and the pressure in this problem is in kilopascals. So we could have the pressure in a variety of units of measurements. And as long as they're consistent within the problem, that is fine to use whatever unit. You don't need to convert it. So the question here goes on to say, what is the final temperature, X, when the volume of the gas is changed to 1880 milliliters, and the pressure is changed to 38.7 kilopascals. So we have 5 bits of information out of the 6. We're going to solve for T2. So you'll notice I'm going to go like this. Okay, so you're going to have, right, this side divided by itself to isolate for x, and we're going to divide this side by that product, which is 35,076. When I multiply these out and divide by 35,076, I solve for x, and that's 566 Kelvin. That concludes our lesson today on the gas laws. That's Charles, Boyles, and the combined gas laws. Have a great day. Bye.